Right now, as your eyes move across these words, something is unfolding in the universe that almost no living human is aware of. A machine no bigger than a small car is drifting through a region of space where no human has ever gazed, no probe has ever ventured, and no scientific model has ever correctly predicted what lies waiting. This is not some new billion-dollar spacecraft. This is not a marvel of modern engineering. It was built before the internet, before home computers, before most of the scientists currently studying its signals had even taken their first breath. It runs on roughly 4 watts of power. To let that sink in, the tiny bulb inside your refrigerator burns more electricity than that. And this ancient, fragile, underpowered machine, one that was originally supposed to die after just 5 years, is right now beaming back information that is quietly cracking the foundations of modern physics. The researchers reading its transmissions are not choosing careful words like curious or unexpected. They are using words like astonishing, baffling, and we were completely wrong. This is the story of Voyager 1, and here is the piece the headlines are hiding from you. It is not just what Voyager 1 discovered out there that should keep you awake at night. It is what that discovery means for the survival of every living thing right here on Earth. It is what is happening to it right now in 2026 that no mainstream news outlet is covering. And it is what is coming in just a few months, a date already carved into the calendar, a moment no human civilization has ever reached before in its entire existence. Stay locked in, because by the time these words end, the night sky above your head will never feel the same again. This channel exists for stories exactly like this one, so subscribe now if you want more, because we are only scratching the surface. Let's rewind to where it all began. September 5th, 1977, a rocket roars off the pad at Kennedy Space Center in Florida, carrying a spacecraft named Voyager 1. The mission plan is small and humble. Fly past Jupiter, fly past Saturn, snap a few photographs, gather some measurements, then drift off into the black and go silent forever. The expected lifespan is 4 years, maybe 5. NASA is quietly preparing to close the mission somewhere around 1981 or 1982. A neat little journey, a nice postcard from the outer solar system, and then nothing. What actually happened is one of the most extraordinary events in the history of science, and almost nobody understands just how extraordinary it truly is. Voyager 1 refused to go silent. It swept past Jupiter in March of 1979 and delivered the first close-up images of that giant world that human eyes had ever witnessed. It swept past Saturn in November of 1980 and kept going, gaining speed, using the gravity of each planet like a cosmic slingshot to hurl itself faster, farther, deeper into the unknown. By the time the 1980s came to a close, Voyager 1 had already flown farther from Earth than any object our species had ever launched, and it was still transmitting, still whispering its thin signal across the widening dark, still gathering data, still functioning on hardware that today's engineers stare at in complete disbelief. Then, in 2012, a full 35 years after launch, something happened that transformed this story into something far bigger than anyone had imagined. Voyager 1 crossed the Heliopause. If that word is new to you, understand this. It is the single most important boundary in our entire cosmic neighborhood, and crossing it is the equivalent of stepping out of everything our civilization has ever called home. Picture it this way. The sun does not just give us warmth and light. It constantly hurls out a river of charged particles known as the solar wind, and that wind blows outward in every direction, pressing against the surrounding cosmos and creating a vast, protective bubble around our entire solar system. That bubble holds every planet, every moon, every asteroid, every comet, every spacecraft we have ever built, and every single living creature that has ever existed. The outer skin of that bubble, the exact spot where the solar wind finally runs out of strength and gets slammed back by the pressure of interstellar space pushing in from the other side, that skin is called the Heliopause. It is the true physical edge of our solar system. Everything inside it belongs to us. Everything beyond it is a completely different universe. And in 2012, Voyager 1 punched through that boundary and emerged on the other side. It became the first object in human history to leave the solar system. Not in a poetic sense, not as a technicality, but the first physical thing our species has ever placed into the actual space between stars. And then it kept transmitting. Think about the weight of that. We have right now a live instrument sitting in interstellar space, not orbiting a planet, not floating in the outer solar system, not hovering near the Heliopause, actually sitting inside the cold, dark, ancient space that stretches between star systems. A space no scientist, no telescope, no ground-based model has ever been able to directly observe from within. And it is beaming us data about what that place is actually like. And what it is telling us is nothing like what anyone predicted. Here is where the first twist arrives. For decades before Voyager 1 reached that boundary, scientists had constructed detailed mathematical models describing exactly what interstellar space should look like. Not wild guesses, but serious, peer-reviewed, rigorously tested models built by some of the sharpest physicists alive. And those models all sang the same tune. Interstellar space, the plasma between the stars, was supposed to be relatively calm, relatively smooth, a thin, cold, empty environment where particles drifted gently and very little happened. Basically a cosmic waiting room between star systems. Voyager 1 walked into that waiting room and discovered it was actually a raging storm. Starting in 2017, the plasma wave instrument on board Voyager 1 began picking up something nobody expected and nobody could immediately explain. A persistent narrow band emission, a kind of faint but relentless hum embedded in the fabric of interstellar plasma that, according to every model built to describe this environment, simply should not exist in the way it does. Not a random burst, not a data spike that could be brushed off as a glitch. A continuous signal, year after year, stretching across a distance of over 900 million miles of interstellar space. To feel that scale, remember that the distance from Earth to the Sun is only 93 million miles. This emission has been detected across a stretch of space 10 times longer than the gap between our planet and our star. Scientists studying the data, published in the peer-reviewed journal Nature Astronomy, were blunt in their conclusion. Interstellar space is not the quiet, uniform void the models painted. It is turbulent. It has structure at every scale, from distances you could measure in meters all the way up to distances measured in millions of miles. It is, in a very real physical sense, alive with motion and complexity that was completely invisible to us because we had never had a single instrument sitting inside it before. Now pause and really absorb that. Every model built to describe our universe beyond the solar system was constructed from the outside looking in, from a planet, using telescopes and equations and theory. And now the first instrument we have ever actually placed inside interstellar space is telling us those models were missing something fundamental, that the universe beyond our solar system is more complex, more dynamic, and more structured than we ever realized. But here is the part that stops being abstract and starts becoming personal, because those discoveries about interstellar space do not stay out there, they come reaching back home. The same bubble that separates our solar system from that turbulent interstellar environment is the exact same bubble that protects life on Earth. The heliopause is not just a line on a scientific diagram. It is a shield. It deflects the most dangerous forms of cosmic radiation, the high-energy particles streaming in from distant exploded stars, from smashing into the inner solar system at full strength. If that shield were significantly weaker or more unpredictable than our models suggested, the consequences for biology on Earth would be enormous. And what Voyager 1 is revealing is that the interstellar environment pressing against that shield from the outside is more turbulent, more variable, and more energetic than any model has ever accounted for. We do not yet fully understand what that means for the long-term stability of the shield itself. But the fact that we now have to ask the question at all is a massive shift in how we understand our own fragility as a species. And now the story gets stranger, because before we get to what Voyager 1 discovered at the boundary itself, we need to talk about what happened in 2023. Because in 2023, Voyager 1 nearly died. For 5 straight months, the spacecraft kept transmitting a signal back to Earth, but what it was transmitting was pure gibberish, corrupted code, scrambled data that the engineers at NASA's Jet Propulsion Laboratory, after decades of experience reading everything this spacecraft had ever sent, could not decode. The instrument was still alive, the signal was still arriving, but whatever it was trying to say had become completely unreadable. For a team that had been successfully operating this mission since 1977, this was unlike anything they had ever faced. The cause, once they finally uncovered it, was both simple and devastating. A single memory chip inside the spacecraft's flight data system had physically deteriorated after nearly 5 decades of relentless bombardment by cosmic radiation. One tiny piece of 1970s hardware, one chip measuring just a fraction of an inch, had developed a fault that was corrupting the section of software responsible for formatting and transmitting scientific data. No alarm had triggered, no warning had come. The chip had simply quietly failed after 46 years of non-stop operation in the harshest environment any human-made object has ever endured. In any normal engineering situation, you fix a broken component by physically going to it and replacing it. In this situation, the component was 15 billion miles away, unreachable by any known method of transportation, with no possible repair mission on any time frame that would matter. The only available tools were radio signals traveling at the speed of light, and even those signals took 22 hours one way to reach the spacecraft. 22 hours just for the message to land. Another 22 hours for any response to travel back. Every single diagnostic step, every attempt to probe the problem, every test of a possible fix required a minimum of 44 hours to complete a single round of communication. Think about what that engineering process actually looked like from inside the control room. You stare at a piece of data. You form a theory about what might be broken. You write a set of instructions designed to test that theory. You transmit those instructions. You wait 22 hours. You receive whatever the spacecraft sends back. You analyze the response. You notice something slightly different than expected. You form a new theory. You write new instructions. You transmit them. You wait another 22 hours. You continue this dance step by patient step for months, and every single moment of that process carries the terrifying weight that a single wrong instruction sent once across 15 billion miles of void could permanently kill the mission with zero possibility of recovery. The team at JPL worked through this ordeal for months, carefully, methodically, under a kind of pressure that most engineering situations never generate, and they succeeded. They realized the corrupted code could not be repaired, but it could be relocated. The affected chunk of software was split into smaller sections and stored in different locations across the spacecraft's available memory. Each section individually checked and rewritten to function correctly from its new home, then carefully stitched back together to operate as one whole. It was, in effect, brain surgery performed remotely through a 44-hour time delay on a machine nearly 50 years old, sitting 15 billion miles away. In mid-2024, Voyager 1 came back online and began transmitting clean, readable, complete scientific data once again, and what it immediately started sending back was more evidence of those persistent, unexplained plasma oscillations in interstellar space, more measurements of that turbulent structure the models had never predicted. The spacecraft that should have died in 1981 had crawled back from what could have been its final silence. And it came back with more secrets to share. But none of that, not the discoveries, not the near death, not the miraculous recovery, prepared anyone for what Voyager 1 had actually stumbled upon at the exact moment it crossed the Heliopause back in 2012. Because this is the part of the story that scientific papers describe in language that stops feeling like physics and starts feeling like something else entirely. For decades, the models describing the Heliopause, the outer edge of our solar system, predicted exactly what crossing it should feel like to an instrument moving through it. The solar wind on the inside gradually thinning out, the interstellar medium on the outside gradually becoming detectable. A slow, smooth transition from one environment to the other. A gradual blending at the edges, like the place where a river slowly meets the open sea. That is not what Voyager 1 encountered. At the Heliopause, the particles were not thinning out gently. They were racing at speeds approaching a significant fraction of the speed of light. They were slamming into each other with energies that generated temperatures approaching 30,000 degrees Celsius. Not inside the sun, not inside any star, but at the outer edge of our own solar system, in what was supposed to be relatively cold, sparse, transitional space. Some researchers have described this region as a wall of fire, and not fire as a poetic metaphor, but a genuine concentration of ultra-energetic charged particles forming a physical barrier at the boundary of everything we call home. And then came the magnetic discovery. For decades, one of the bedrock predictions about crossing the Heliopause was that the magnetic field environment would shift dramatically. Inside the bubble, the sun's magnetic field. Outside the bubble, the completely separate magnetic field of the galaxy. Two distinct environments with distinct magnetic personalities, cleanly divided at the boundary. Voyager 1 found something entirely different. The magnetic fields on both sides of the heliopause were, in ways existing theory had never predicted, connected. The sun's magnetic field lines, carried outward by the solar wind and compressed at the boundary, were interacting with the galactic magnetic field outside in a process called magnetic reconnection, where field lines from different sources rearrange themselves and release energy in the process. The solar system and the galaxy surrounding it are not magnetically separate, they are magnetically linked. At the boundary between everything we know and everything we have never explored, there is a zone where energy is being traded between our home and the wider cosmos in ways that every model built before Voyager 1 crossed that boundary had simply never accounted for. This is not a footnote. This is not a minor correction to existing theory. If the relationship between the solar system and the interstellar environment is more dynamic, more connected, and more energetic than the models described, then our understanding of how the heliosphere protects Earth over geological timescales needs to be rewritten from scratch. Now, let's talk about what is happening right now in 2026, because the story is not over. It is, in fact, entering what may be its final chapter, and the timeline is far tighter than most people realize. Earlier this year, NASA made a decision that nobody inside the mission wanted to make. The low-energy charged particle experiment, one of Voyager 1's scientific instruments that had been collecting data almost without interruption since the spacecraft launched in 1977, was switched off. Not because it stopped working, it was still working perfectly. It was shut down because Voyager 1 is running out of power, and there simply was not enough left to keep it running. Voyager 1 draws its power from 3 devices called radioisotope thermoelectric generators. These are essentially containers of plutonium-238 that produce heat as the plutonium slowly decays, and that heat gets converted into electricity. At launch, these generators produced around 470 watts of power. Today, nearly 49 years later, they produce roughly 250 watts. They bleed about 4 watts every single year. At some point in the early 2030s, the output will fall below the minimum threshold needed to run any remaining instrument at all, and Voyager 1 will go permanently silent. The team managing the spacecraft has known this reckoning was coming for years. Years ago, the scientists and engineers gathered together and mapped out a careful plan for which instruments to shut down and in what order to squeeze every last drop of scientific value out of the dwindling power supply for as long as humanly possible. Of the 10 scientific instrument packages Voyager 1 carried when it launched, 7 have already been powered down. The decisions about what to switch off and when are among the hardest choices any scientific team ever has to make, because every instrument lost is a set of questions that will never be answered, and because there is no way to turn an instrument back on if you later realize you shut it off too early. But here is the twist that almost nobody outside the JPL mission team is talking about. They have not given up on buying more time. Engineers are currently working on something they have reportedly referred to internally as the Big Bang procedure. It is an experimental attempt to restructure how power is distributed across Voyager 1's remaining systems in order to squeeze additional electrical capacity out of components currently operating at lower efficiency than they could be. The idea is technically complex and carries real risk because even tiny changes to how power flows through a nearly 50-year-old spacecraft with no manual override available could produce unpredictable results. So the team is doing what careful engineers do. They are testing the procedure first on Voyager 2, which carries slightly more available power and sits somewhat closer to Earth, making any potential failure slightly less catastrophic. Tests on Voyager 2 were scheduled for May and June of 2026. If those tests prove the procedure is safe and effective, the same approach will be attempted on Voyager 1, with the earliest possible attempt scheduled for no earlier than July of this year. And here's the detail that makes it truly significant. If the procedure works, there is a real possibility that the low-energy charged particle instrument, the one just recently shut down, could be switched back on. The team is cautious. They are making no promises, but they are still fighting, because when it comes to Voyager 1, the history of assuming things were finished before before they actually were has never once aged well. And now comes the moment on the calendar, the one already locked in, already certain, the one no human civilization has ever reached before, and that will arrive whether anyone is paying attention or not. On November 18th, 2026, at 16 minutes and 12 seconds past 2 in the morning Pacific Standard Time, Voyager 1 will reach a distance of exactly 1 light day from Earth. That means it will be so unimaginably far away that a signal traveling at the speed of light, the fastest anything in the universe can move, will take exactly 24 hours just to reach it. If you send a command to Voyager 1 on a Monday morning, you will not know if it arrived until Tuesday morning, and you will not receive the spacecraft's response until Wednesday morning. 2 full days of waiting just to complete a single exchange of information. No human-made object has ever been that far from Earth, not once in the entire history of civilization. And on that date, in November 2026, Voyager 1 will cross that threshold for the very first time while it is still alive, still transmitting, still sending back data, and then it will keep going. Every hour it travels roughly another 38,000 miles deeper into interstellar space. The communication delay will keep growing, the power supply will keep shrinking. And at some point in the 2030s, the last signal will come. But even when that happens, Voyager 1 does not stop. There is nothing in interstellar space to stop it. No friction, no atmosphere, no gravity strong enough to pull it meaningfully off course. It will just keep drifting silently in a straight line at 38,000 miles per hour into a darkness that has no end on any human timescale. And bolted to its frame, attached to the body of this dying machine, is something that will outlast all of it. The Voyager Golden Record, a gold-coated copper disc carrying greetings spoken in 55 human languages, the sound of rain falling through a forest, the sound of ocean waves crashing on a shore, the sound of human laughter, 90 minutes of music chosen from cultures spanning the entire history of human civilization, diagrams explaining the basic principles of our physics and mathematics, and a map made from the positions of pulsars, designed to show whoever finds it exactly where in the galaxy our tiny planet sits. Carl Sagan, who helped design the record, described it as a message in a bottle cast into the cosmic ocean, and that is exactly what it is, because whoever or whatever eventually stumbles across it, whether that is another civilization a million years from now, or some form of intelligence we cannot currently imagine, the record will tell them something true, that there was a species here, that they were curious, that they reached, that they built a machine from metal and electricity and mathematics and hurled it beyond everything they had ever known, carrying the sound of their own laughter. The record will still be traveling when the sun has swollen into a red giant and swallowed the orbit of the Earth. It will still be traveling long after every human city and every human archive and every piece of stone we ever carved our names into has been erased by geology and time. It is the most permanent thing our civilization has ever created, and it is riding on a spacecraft that currently runs on less power than the light above your bathroom sink. Now come back to the science, because there is one more thing Voyager 1 is doing right now that deserves to sit at the very center of this story. The persistent plasma emission it has been detecting since 2017 is not just an anomaly. It is, according to the researchers analyzing it, the first continuous real-time measurement of interstellar plasma density that humanity has ever obtained. Before Voyager 1 started detecting this emission, scientists could only take isolated snapshots of plasma density in interstellar space. Measurements triggered by specific events like shocks produced when giant eruptions from the sun traveled all the way out to the Heliopause and sent ripples into the interstellar medium. Those measurements were valuable but scattered, like trying to understand what the weather is like across an entire continent by checking a single thermometer once a year in one city. What the persistent emission from Voyager 1 is providing instead is something closer to a continuous feed, a running portrait of interstellar plasma as the spacecraft moves through it day after day, year after year. And what that portrait is revealing is that interstellar space is not a static, uniform background. It has texture, it has weather, it has structures built from charged particles and magnetic fields that stretch across millions of miles and interact with the outer boundary of our solar system in ways that models built from Earth could never detect or predict. The space between stars is not empty. It is full. It is active. It has a physical personality that we are only now, for the very first time in human history, beginning to actually read. There is a question sitting at the center of all this that the scientific community has not yet been able to answer. The persistent emission has two possible physical explanations, and researchers working on Voyager 1 data have not yet been able to determine which one is correct. The first possibility is that the emission comes from thermally excited plasma oscillations, the natural vibration of plasma particles interacting with their surroundings. This would be a genuinely significant discovery, but it would fit inside existing physical frameworks without demanding they be rebuilt. The second possibility is that what Voyager 1 is detecting is something called quasi-thermal noise, a different physical mechanism that carries information about plasma density and temperature in a subtly but importantly different way, one that would require existing models of the interstellar medium to be substantially rewritten. Distinguishing between these two explanations requires either additional data from Voyager 1 itself, which is producing less of it every year as more instruments are shut down, or a new mission specifically designed to study interstellar space with instruments built for exactly this purpose and capable of making the measurements needed to settle the question. No such mission currently exists. No such mission is currently funded. The next spacecraft capable of reaching interstellar space and crossing the Heliopause, if it were funded and built and launched today, would not arrive at that boundary for at least 25 years, which means when Voyager 1 finally falls silent, the question it raised will still be wide open. The map it started drawing will stop being updated. And the only real-time window into interstellar space our civilization has ever opened will close and stay closed for decades. That silence is coming. The exact date is not fixed yet, but the direction is. Every year the power drops. Every year more instruments go offline. Every year the team at JPL makes harder choices about what to keep running and what to let go. And somewhere in the early 2030s, the last instrument will reach the minimum power threshold, and the last signal will begin its 24-hour journey home and arrive and be recorded, and there will be nothing after it. After that, Voyager 1 will just keep moving silently at 38,000 miles per hour, carrying its golden record through the darkness, passing through regions of the galaxy that human eyes will not reach for tens of thousands of years, continuing the journey that began on a morning in September 1977 when a group of engineers pointed a machine at the stars and pressed the launch button, expecting it to last 5 years. Here is what I want you to take away from all of this, because there is a fact sitting in the middle of this story that is easy to miss when you are focused on the discoveries and the physics and the engineering. Right now, in 2026, the only live scientific instrument that humanity has ever placed in interstellar space is 48 years old. It was built using technology that predates personal computers. It is powered by less electricity than the light above your kitchen stove. And it is sending back information that is rewriting how we understand the universe and our place inside it. We have built things that are much larger. We have built things that are much more powerful. We have built things that cost far more money and involve far more complex technology. And none of those things have told us what Voyager 1 is telling us right now, because none of those things had the one thing Voyager 1 had. None of them had the audacity to keep going long enough to actually get there. There are questions about the universe that can only be answered from inside the universe, not from a telescope on the ground, not from a satellite in Earth orbit, not from a mission to Mars or the asteroid belt, only from a machine that crossed the Heliopause and entered the space between stars. We have exactly one such machine. It is old and dying and running on 4 watts of power. And as long as it is still transmitting, we need to be listening, because when it goes quiet, the answer to some of the most important questions we have ever asked will go quiet with it, at least for a generation. The signal is still coming, stretched across 15 billion miles, delayed by 22 hours of travel time, carrying information about a universe that is stranger, more turbulent, more connected, and more extraordinary than any model built from Earth had ever correctly described. One machine, 4 watts, one chance to listen. The question is whether anyone is paying attention. If this kind of story is what you come here for, subscribe right now and turn on notifications, because we are going deeper into the edges of what science actually knows next time. Drop a comment with what surprised you most in this video, and share this with someone who needs to hear it, because this story deserves far more than the silence it is currently getting.